record to the cloud.
Take this chair and move it over so that he's moving around.
Hey guys, welcome back to my course. Okay, so, oh, the projector is not working. Let's see. Oh, I plugged in the wrong cord. Right, so a couple of just one administrative thing. The homework is out. I love this homework for so many reasons. As I was posting it and looking, because I created it last year, and as I was looking at it, it occurred to me that I don't want to see myself. It occurred to me that, oh, can I get someone to tilt the thing a little bit down? Thank you. Yeah. ACA, hope you're enjoying London, man. You're relieved of your duties. All right. Hopefully the audio is coming through for you guys. If not, I'll find out after the fact.
That wasn't so easy, does it? Right? You made it look easy. Yeah.
This is gonna make for great viewing.
I'll move it the other way. Oh, they're only gonna see the.
I was just gonna say.
Yeah, just gonna be a regular screen. They can't
Oh,
see
right,
anything.
yeah, of
A
course.
long pause for
Duh.
Yeah.
How do you get there? Anyone else want to try before
What's happening right now, guys, is that we're trying to move the projector in place.
In the format, man.
How is it that, like, who installed this? Or maybe it's just my computer, I don't know. Oh, wow, that's. Yeah, that's fine. Let's do that. Okay, so I posted homework 1, which has 2 parts, an analytical part and a MATLAB coding part. The goal of the 2 parts is that you're able to validate, you're able to solve the problem analytically in part A, and then part B, you write like you control flow of your program matches the rules of the game, which are all the information needed are in the instructions. And hopefully by doing a Monte Carlo simulation of gameplay 1,000 times, you get the probabilities of winning that you derived in part A. So if you are not very experienced in programming, I would suggest getting started on the assignment early. And I do start you off with a lot. I actually give you a lot of code. Basically, the assignment is to fill in a few blocks of code, which is how it's going to be in this course for the most part. So I would not try to, don't modify the lines of code that are there unless you're really stuck, because the lines of code that are there to make your job easier. So don't try to write it from scratch unless if you already did it, that's okay. If you got the solution, that's fine. That's great. I'm just saying that you do not need to. The way I did this is I wrote the program last year when I solved it. I wrote the program And then I just took out a few lines and gave it as an assignment to make sure that, you know, to make sure that it's easily doable by a grad student without a ton of programming experience. And I believe it's due not this coming Sunday night, but the Sunday night after that. It's a fun assignment, and I think it's I think it's a good way to just learn a little bit of Monte Carlo. So Monte Carlo methods are hugely useful because like they rid you of the need to perform integrals, for example. If you have a complicated integral, you can just sample it very, very many times, and you can construct a Monte Carlo approximation of a complicated integral. It's also useful in these cases where you want to understand, like if you want to get a confidence interval in some measurement, or if you want to know what are the chances that that of some outcome happening. If you know the rules governing a generation of that outcome, you can just run it many, many times and count the number of times the outcome happened. Okay, so with that said, we're done with probability. I think I've taught you all the probability you need for this course, namely the fundamental rules and Bayes rule. You will have a little bit more in Bayesian decision theory, but we're going to do that after covering logistic and linear regression. Today, what I want to do is give you a crash course on linear algebra. And I'm going to try to do it a little bit differently than last year. I'm going to try to give you the context. I'm going to try to give you a better idea of why linear algebra is so important for machine learning. And so I'm going to advance the screen. Okay. Right, so we're going to deal with three cases of multiplying matrices and vectors. And so remember I said that machine learning is all about X and Y. Oh, there's a point on this. Okay, so remember X is called the feature vector. It's called, sometimes called your input. That's your data. Those are the set of predictors. And in this case, X is just a vector. It's a row vector in this case. It has one row and D columns. So the one row, so the rows in X are going to correspond to examples. And the columns are going to correspond to the dimensions. So let me think of an example here. Let's say I'm trying to predict whether a tumor is, let's say a tumor, we're still good though. X, we want to predict whether a tumor is benign or malignant. We perform a biopsy. We biopsy one tumor, one mass of tissue, and we collect D measurements. And we put those D measurements into vector X. So the D measurements here maybe can be the mass, the diameter, volume, asymmetry, anything that you want to throw in there. And the things that you throw in there are things that a priori you believe are going to discriminate between benign and malignant tumors. So that's going to be, in this case, we have one example, we have one biopsy. And that's going to be our vector X. And now in classification, in supervised learning, which is the most popular subset of machine learning, we're going to be multiplying that vector X by another vector that I'm going to call W. And I chose W for a reason. The W here is like conventionally used to signify weights. W is a weight vector. And so what W is doing is it's assigning a scalar weight to every one of those biopsy measurements that I defined in X. And so, this is, I'm about to switch on the board, but before I do that, let me just finish up on the slide. So this is, what is this operation called? So the product of X and W yields just a single number, in this case, Y. So what is that operation called between X and W? Dot product, yeah, or inner product. Because it's taking two vectors, and it's essentially, geometric view is that you're projecting X onto W or W onto X, and what comes out of it, the number Y, which is really, this is called the soft prediction in classification. I'll tell you why it's called soft in a second. It's called the inner product or dot product. It's really just more generally, it's a multiplication of two matrices. But here, the matrices are a row. X is a row vector and W is a column vector. And so, what's happening in words is that a vector of D features is being linearly weighted and summed by D weights to produce a continuous real number, right? So what's implied here is that X is a real vector. It doesn't have to be real, and oftentimes in machine learning, X is binary. However, W is never binary. W is free to vary to, it can be negative, positive, any magnitude. And as a result, Y is always, Y is also a real number here. And so I'm just going to write this out. Hopefully this, okay. I don't know if this is going to work for the people, but I'm going to write this up for you guys at least. Yeah. A little bit creepy. But, so this is our X. And I know that for some of you, this is going to be too basic, but I've learned that it's better, especially for something like this, it's better just to make sure that everybody understands what's happening. So we have our and so is equal to, it's not too bad. And so mathematically, that is written as Y is equal to the sum across. I'm going to put W first for a reason. It's a summation of products. This is giving you all the views here. And then finally, you think geometrically, this is. So,
I think the board's backwards, by the way, on the screen.
Can I change that? Why is that?
You might have to switch that on Zoom. Right?
Oh, thank you. Yes, that's what it is. Touch up my appearance all the way to the max. Always. No, I'm just kidding. All the way to the max, baby. Come on, why is that even an option? All right. So, right. So this is like, this is mass, maybe. This is volume. This is surface area. and this is maybe asymmetry, some measure of asymmetry. And so the key thing is that in machine learning, these two are in your what's called the training set, and that's you collect that data, right? And W is the thing that you want to learn. And so hopefully you can see that you this number, if you want to choose your W's, so that if you look at like a distribution of Y, hopefully you'll have a picture like this, where you want to choose your Y so that for every X vector that is benign, that gets weighted to a smaller value of Y than X's that are malignant. So you see that it really comes down to this inner product. This inner product is like it's central to all of even deep learning. At the core is this operation. It's a transformation. That's what this really is, and you're going to see that in a few slides. It's a transformation of your data from X space to Y space. Okay, and so what was I going to say? So you wanted to. So the other thing to kind of pay attention to here, if your machine learning algorithm works well, then it will. Let's say that asymmetry turns out to be a really important variable for predicting benign versus malignant. What do you think that will mean to the elements of W? If asymmetry is, let's say asymmetry is super predictive of whether a tumor is benign or malignant.
Which one of those two? It'll be higher or lower depending on which of those. So that weighted.
Yeah, so it's going to be, that's right, its
Relative.
magnitude will be high, right?
If it's
So no, I mean the WD will always be high magnitude.
I mean, if asymmetry correlates to benign, will it be much lower than the other another one?
So
Is that the one?
oh,
Be like
I
higher
see what
Y?
you're saying. So basically, it depends on how you define your labels. So we generally, the way it's defined is this is just, and it doesn't matter which way you do it, but this is like the standard. This is a common convention.
No, I meant if asymmetry is highly correlated to being benign, then your WD much lower than the other ones, right? I know that's probably not.
What do you mean by lower, I guess?
A lower magnitude. If
No, it's
more
always going to be high
more
magnitude.
Asymmetry means more benign.
Yeah, so
Why would it be higher?
no, so what I mean is it will either be very negative or very positive. You
I meant
understand?
lower as in
Yeah, lower is in net. So,
Yes.
but zero,
I
but
didn't mean direct.
that's right. So yeah, so the magnitude of WD is going to be high if asymmetry is really important. Now, and the next question is, what if it turns out that mass is not very predictive? What is that going to mean about W1? It's going to be zero, basically. So a really good classifier, and this is we're gonna cover this when I talk about regularization. A really good classifier will set a lot of the weights to zero, and the reason for that is, you know, especially in something. This is not radiology, whatever it's called, oncology. Whoever looks at biopsies, let's say that they start using machine learning on their biopsies. But they want to understand what the algorithm has learned. They want to know what it's using to make its decision. And so the way they do that is they look at the weights. They look at the weights and they also look at the predictions for each class. And so the problem with one way of constraining your model, and another way of saying constraining the model, is inserting prior information into the model. So there's two ways of putting prior information, at least two ways of putting prior information into the model. what method number one is that I expect my weights to be fairly small. Method number two is that I expect a lot of my weights to be 0. Method number two is, so the first method, I guess I'll say it even though it's really, we're ahead of, this is coming later in the course. So, if W is small, that's called an L, and don't worry so much about these terms. If we expect W to have small numbers, that's achieved by imposing an L2 penalty. And the other prior information is that it's sparse. So sparse means many elements of W are going to be 0. That's called an L1 penalty. And the L2 and L1 has to do with the norm of W. There's different types of norms. So the L2 norm is basically just the sum of squares and then square rooted. And the L1 norm is just the sum of absolute values. It's running out. Oops. So basically, this is called an L1 norm. So there's different ways of quantifying the norm of a vector. This is the one they're used to. This is the Euclidean norm. This is like the length of the vector. And so the reason I'm saying this is because in machine learning, what is done is the W's are usually constrained to be either small or sparse. So sparseness, they're both used. Any real machine learning system will have both of these, for sure. But this is better. Sparseness is better. Going back to what I was talking about with the oncologist who wants to know what his machine learning algorithm is doing. He's going to look at the weights. And let's say that all of them are 0 except for W3 and WD. Then he knows that what the algorithm has learned is that surface area and asymmetry are predicting benign or malignant. And the magnitude of those weights is the magnitude of W3 and WD is gonna tell him which of those features is more important. What else did I want to say? There's a caveat to everything I'm saying, but we'll tackle that later. And basically, I'll just mention it briefly. The caveat is that sometimes you weight a dimension heavily because it helps you denoise the prediction, but that feature is not actually important. But we're not considering that example here. In most cases, in the vast majority of cases, the bigger the W, the more informative that feature is. Yeah?
So what happens if one feature is different depending in another feature? So just an example, if you have a green and high area, then it is malignant. But if you have blue and high area, then it's benign.
I see. So what you're saying is that, right, so that's called a nonlinear interaction. So that's like, yeah, if you're asking what I think you're asking, what you're saying is that what you're asking is what happens if the relationship between one feature and the outcome is depending on another feature. Okay, so that's a really great question. So that is the fundamental reason why we do why we implement nonlinear operations in neural nets. So what I've shown you, and we'll get to nonlinear algorithms soon, but so far what I've shown you here is that, so the case that you just outlined will not be handled optimally by this formulation. Now, so human intuition is that, yeah, these like interactions are really important. But surprisingly, in the majority of cases, a linear approximation works really well. Now, for like vision, for computer vision, speech recognition, where you have you have an abundance of data to learn from, and there are nonlinear interactions in those problems. They're definitely necessary. But the way that's handled is by essentially, instead of, so it would not really, you would need to have, this is just a single, so sigma is going to be a nonlinearity, something like a sigmoid. What the sigmoid will do to this is transform, this is a real number, it's a continuous number. The sigmoid, essentially, any nonlinearity will push the output into either a 0 or a 1, so either on or off. So what you'll have in your case, I don't remember the example you gave, but basically you'll have two of these sigmoids, and you'll have like, is it green or is it blue? And the other one, is it asymmetric or is it not? And basically what these nonlinear operations allow you to do is they allow you to implement logical operations with mathematical functions. So they'll be like in a gate. So like, what the neural net will do is, if it's blue and it's asymmetric, then it's this. If it's green and it's asymmetric, it's that. So, and they do that with, this is basically a gate. So I don't know if you guys are familiar with like logic gates and circuits. But basically, our computers are organized in binary. So everything is either, it's a 0 volts or 5 volts, 0 or 1. And so neural nets kind of approximate that. What I've shown you so far is just this. So this is called a soft prediction. So this is before the nonlinearity. But that's jumping ahead. But basically, at this point of the course, the answer to your question is we don't handle that yet, but we will. Okay, so I'm going to switch. What do I want to do? Share screen. Okay. The next case, we have 3 cases to cover. Okay, so now we've expanded our problem to X being a matrix. Okay, so in our problem, what's happened now is that instead of having 1 tumor biopsy, we have N. So I've now collected N biopsies and measured the D features for each of them. And I'm going to apply a weight vector W to each of those biopsies. So I'm going to weight the same features in every one of those samples, and I'm going to produce a prediction for each biopsy. So in linear algebra, we have an n by d matrix that's multiplied by a d by 1 vector. And hopefully you remember from linear algebra that the product of a matrix and a vector is another vector. So, and I don't like the way they teach this, because the way they should teach it is what this really is. This is a transformation. So basically, geometrically what's happening is you're transforming a piece of data, some data set, from one space into another space. So what the W vector is doing is it's mapping a d-dimensional data point into a one-dimensional data point, right? So every one of those biopsies lives in D dimensions, and your classifier W comes in and it condenses it into a single dimension. And so I'll talk over it while I erase this. One of the things that I haven't mentioned yet is that a big reason, if machine learning didn't exist, we didn't have the formalisms. Somebody could take the D measurements of the biopsy, an oncologist, and kind of look at them, see what they are, and kind of intuit a rule, right? A rule for transforming, mass, volume, surface area, and asymmetry into his best prediction as to whether this is benign or malignant. And I would argue that what is happening in the brain is kind of similar to what this is doing. What he's doing, he or she are doing is kind of weighting all the information together into a single prediction. And the other thing I wanted to say was that the features of D, the different, like there's going to be correlations among the features, right? So generally, if the volume of a tumor is higher, then its mass is also going to be higher. And so by that logic, we don't, we want to exploit the redundancy. We don't want to, we want to be able to combine features that are redundant. So if mass and volume are redundant, then W1 and W2 will each be equal to +1, and we'll collapse mass and volume into a size variable, for example, something like that. And this is like, again, this is the essence of classification. Is combining features that are redundant into like a meta feature. Okay, so now my X is a matrix where each element of the matrix corresponds to one feature of one biopsy. And so now the big difference is that we've extended our problem from a dot product, which just looked at a single biopsy, to a matrix vector multiplication. Oh, actually, I should draw this different size. So the y vector is n-dimensional. This is important. It's not d-dimensional. You can miss that here because of the sizes that I've drawn. I didn't pick really great, but in general, you want, this is another really important thing. You want n to be bigger than d, if possible. So n is a number of examples, and d is the number of features. So this is something that in any machine learning application, people have to discuss this, how to pick d, how many features should we throw in? And they ask things like, do I have enough data to fit this model? The first thing they look at is how many examples do I have compared to how many dimensions is my data? And so, the general rule of thumb, and this This really depends on how noisy your data is and all kinds and what architecture you're using. But you want to have at least as many examples as dimensions. If you think about a linear system, you need to have at least, to solve a linear system, you need to have at least as many equations as you have variables. So roughly speaking, the same kind of relationship holds. You don't want to create, you don't want to fit a 1,000-dimensional neural net when you only have 10 examples.
If you don't have enough dimensions, how could you solve it though? I mean, if you have dimensions that you can't solve for, then the system doesn't describe what's actually happening.
So it will wait. If I have a data set, let's say I have, let's say my biopsies are 1,000-dimensional, but I only have 10 of them.
Right.
5 benign, 5 malignant.
You could still predict what's
I
going
can still fit a model. I guarantee you it's not going to work. It's going to overfit. So it's going to do a really good job at getting at predicting those 10
Right.
correctly. It's going to get I guarantee you 100% accuracy. Why? Because it has 1,000 degrees of freedom. It has 1,000 weights to classify 10 examples. That's easy.
Then you can't. how could
But
you
then
get that?
when you get a new biopsy, it will fail. Right. So n is the number of examples, and d is the number of dimensions. And what the matrix math is doing, I'll write this out. So this is what they teach you, right? That to multiply a matrix by a vector, you're going across the row, and you're multiplying x11 by w1, then adding that to x12 plus w2, all the way through x1 becomes w2. Right. And in MATLAB, like if you wanted to, in MATLAB notation, this would be something like, no, it would just be yn. Y would be equal to x times w. That's the beautiful thing about MATLAB, is that it's so, it's so intuitive. The syntax is so intuitive. What was I going to say? Yeah, so what this is doing is applying a single weight vector to every one of your biopsies. And now hopefully you understand that, for all some of these, each row is a biopsy. So some of those will be, some of the rows will be malignant. Let's say that row number 2 is malignant. Maybe some other row is malignant. You'll generally have a class imbalance. And let's say that row 1 is benign and row n is benign. The goal of W is to separate the reds from the greens. Right? So we'll want the greens to kind of have values that are small, and we'll want the reds to have values that are large. And this is your y dimension, right? So you want your projection vector W to learn how to discriminate the reds from the greens. Okay, so that's straightforward. Okay. Yeah.
If I understood correctly before, you said this is used for eliminating redundant parts of the dimension. How is that?
Yeah, so right, so let's say that you have, let's say the dimension 1 and dimension 2 are redundant. what it's going to do is if it will learn to make, if W1 ends up being equal to W2, then not sure how convincing this is going to be, but let's just call it W naught. That's good. So W naught is going to equal to W1 and W1 and W2. So W1 and W2, if they come out equal, what you end up doing. I didn't need a parentheses there. What you end up doing is that you've transformed your problem essentially into a two-dimensional problem, because W1 and W2, by being equal, effectively you're multiplying the sum of those two dimensions. And so it will learn that. It will learn that by trying to separate those distributions, it will learn to choose values for W that get rid of basically. So it will not, for example, try to make, the biggest thing is that you don't want these to have the opposite sign if they're positively correlated. If X1 and X2 are positively correlated, you want W1 and W2 to have the same sign. That's the key thing. All right. Stop share. Oh, share screen. Okay, so our third case, and this is the most interesting one. Okay, so now I have n biopsies with D features, just like before, but now I have W being a matrix. So what could that mean? So what is the interpretation? So now Y is also a matrix, right? So this is n by D, so n biopsies, n samples, D dimensions, and I'm going to call K filter. The dimension K is number of filters. Sometimes it's called kernel. Sometimes it's called, there's so many names for this variable K. Factors, components, filters, kernels, it's probably more. But I like filters because that's what's used in Keras. And the dimensionality of the product Y is n by K. So now each biopsy has been defined not by D features, but by K numbers. I'm just going to call them numbers for now. So can anyone guess what this means in words? We know what it means mathematically. Generally, K will be less than D. I'll say that. But not always. There are applications actually where K is specifically chosen to be bigger than D. But generally, K will be smaller than D. So what is this? What is it? What are the columns of W doing? We know that we saw that the rows of W here are weighting the, basically assigning a weight to every feature.
Okay, could you separate the values that are between the banana and the malignant so that it's more clear?
That a single W could do that.
You're predicting something else that's not related to the first one.
Like pretty much. Exactly. So what you are doing is, one way to think about it is an intermediate variable. For it's more abstract. So and of course now I've set myself up to try to define some abstract variables.
Be like you have benign, malignant, and like severity. Could that be a different variable?
So whatever variable K would refer to, it has to be something more interesting than mass or volume, but ultimately less high level than benign or malignant. So let's think about, yeah, I mean, is it, what did you say? Severity?
Severity, like,
I mean, what would that be though? What would severity be for?
be like a coloring. I don't know.
Yeah, maybe,
exactly.
I mean, I don't know, but how about atypicality, for example? So it's a measure. What we're basically trying to do with the K dimensions here is we're trying to learn we're trying to learn multiple representations of a biopsy. And the basic idea is that each one of those K representations is going to be informative as to the thing we ultimately care about, which is benign or malignant. And so, for example, the first column could maybe the first column of W would maybe be trying to predict. Other than it, let's try to think of two examples. So atypicality is one. So that's definitely something an oncologist probably has like a representation in their brain as to like how normal does this tumor look? Like, have I seen this tumor many times before? And maybe let's just take color actually, even though maybe color wouldn't follow from mass and volume and asymmetry, but let's say color is actually a good example. So why is now let's say, and now will be K is equal to 2 in that example where the K's are atypicality and color. So now each tumor, instead of being defined by mass, volume, surface area, really low level features, is now being represented by more abstract variables that we believe are going to do a better job of predicting benign and malignant.
Aren't measurable and therefore not put next in the first place.
So they're right. So the thing that we can measure X, but Y is now not observed. The Y's are not observable. They're learned. They're learned combinations of W. And so it's like if the one way to think about it is if X, let's take the case of a single tumor, and this will work better in 3 dimensions, but I'm not going to try to talk
about a training set.
What's that?
So you're not talking about a training set right now.
Nope. I mean, the X is the training set. Y is now is actually part of the learning stage. So let's say that this is your tumor, X, it's a vector. And let's say that what we're doing geometrically is we are going to make not one projection, but 2. And again, think about this and this is X is multidimensional. So this is W1 and this is W2. You're essentially projecting the vector X onto 2 dimensions, and maybe dimension 1 will measure typicality and dimension 2 will measure color, for example. And so instead of having 1 dot product, for example, you have 2 dot products here. So before I switch to the board to write out the matrix multiplication equation, what's happening here is that a matrix of n examples and d features is linearly weighted and summed by d weights with k filters. So one way to think about this is now you just have multiple weight vectors instead of just one.
So this is what we were talking about, like, is deep learning, right? So that like each
It's not even deep learning yet. Right now, it's just deep learning would be it would be like if first you apply W1, then W2, then W3, and you do that many times. But this is just transforming your data into more than one dimension, where each dimension is a combination of your original measurement. So X is the thing that you can measure. And Y is the thing that you're going to learn via W. So the equation for this, so now W is going to be vector writing here. And so now so that's my, let's see, something like this. This is it. So you're multiplying the element in at row M and column N of Y is equal to, so this is a multiplication of row M of X by column L of W. So it's like this by this, for example. So again, that's what they teach, and it doesn't give you any insight into what's happening geometrically. What's happening geometrically is that you're projecting your data from a d-dimensional space to a k-dimensional space. So in the histogram picture, you'll have kind of one distribution for every k. So you'll have 1, 2, and maybe k, and then you'll have some dimensions. These are my benign and malignant. And so each of these filters, aka columns of W, are going to produce some separation between, hopefully produce some separation between benign and malignant. And by the way, the other thing I should have said is that when you actually do this, you just learn the elements of matrix W, and interpreting them, you have to just look at them. But the typicality and the color examples, like those are obviously not specified. Like there's no guarantee, first of all, that'll happen, and it's up to you to look at the weights and try to basically interpret them. So all the algorithms are trying to do is just separate benign and malignant as much as possible. But the idea is that each of these, each of these k vectors is giving you another dimension, another combination of observed variables that where there's a discrimination between benign and malignant. And so now your y, which is not here, but it was on the slide, your y is now one row vector for every example. Okay. Let's see, we have a little bit of time left. So what I'd like to do is go to MATLAB. So, I'll sit here. What I want to do is just kind of give you another, I know I've used a benign and malignant example in this class, but what I'd like to do now is just bring in a data set and kind of illustrate this with an example. So MATLAB has a lot of built-in data sets. They're toy data sets, but there's some of them are real. And so if you want to see what they are, okay, if you just type in, if you go to the command window, you can see all the someone, wait a second. These are mine. Let me see. That was awesome. That was a function. Functional connectivity k-means. So here we go. All I had to do was type the letter A. Would have saved myself that embarrassing moment that's captured now on Zoom and Dropbox. Thank you, technology. So here are all the examples. Here are all the, and actually, I think there's a way to, did I search? Oh. If you just search, MathWorks is just, they're so well documented. That's probably the biggest difference between MATLAB and every other language. Is just the documentation for MATLAB is so extensive. So here we go, like flu rates, bacteria counts, hospital simulated data, all kinds of data that you can pull in to play around with. Another, by the way, I'll just say this now for the course project, a really great site, Kaggle. Yeah, exactly. I mean, when I first started teaching this course, I didn't even know this was even available, but let's say I'm interested in cryptocurrency data. So I go onto Kaggle and there's like, there's all kinds of data that are posted, and they make the person give you some documentation. So this is like, these are, I guess, at prices of the different cryptocurrency, what do you call them? I don't want to, securities, if they're called securities over, their value over time. And so there's lots of data for you to play with online, as well as in MATLAB. Here, what I'm going to do is load in this arrhythmia data set. And the command whos tells you what is in your workspace. So I've loaded in this arrhythmia data set, and I see that I have 4 variables. And nicely, I have an X and a Y. So like I said, machine learning is all about X and Y. So as you can guess, well, actually, let me ask you, how many dimensions are in the arrhythmia data set? 279. And how many examples? 452, right? And obviously, it's important to know what the dimensions are. And the dimensions are, this is ECG data, I believe. So I don't know if, and also demographic data. So for example, the age, right? So the goal of this is to predict, take an ECG or EKG, I get them confused, but take in an EKG and try to predict whether the person has arrhythmia. And so here are some of the measurements that they took from these people, from these 452 individuals. The gender, the height, the weight. So for example, let's say that BMI is correlated with arrhythmia. Then what a smart classifier will do is it will learn to kind of ideally take a ratio of weight to height. But even if you just like subtract height from weight, like if weight minus height is a large number, maybe that's correlated more with arrhythmia. So that's like that's like an example of how you would combine features. And then all these other features are like, it's actually pretty impressive. They hand labeled all these features of the waveform. So like there's different components of the QRS complex is like the standard heartbeat, right? You guys know this probably from Bixen's class. Those of you that were fortunate enough to attend undergraduate studies at the City College of New York. Anyhow, so so you need to know what the features are, right? Generally, I mean, you don't need to, but it's definitely going to help you as a practitioner. And so let's visualize the X first of all. And actually, the first thing I do generally is I look at, oh, right. This is a sixth, right. So this is the first thing I do. Unique Y tells you all the unique elements of the Y. That's the thing you're trying to predict. And so this is almost a 16 class problem, but they say, let me see. So they tell you what these, right. So 1 means no arrhythmia. 2 to 15 means some class of arrhythmia and arrhythmia. And number 16 means they undetermined, or when the Apple Watch tells you we can't, you do your EKG and you say yes, tell me if I have an arrhythmia, and then you do it and they're like, oh, we're not sure, and they put all that stress into you. So that 16 is like that. So one way I would do this is what I would do right off the bat. I'm gonna convert this into a binary classification problem. I'm gonna say, so this line of code here, so the equal sign in programming is not equal, it's assignment. So this line of code means assign everything to the right of the equal sign to variable YB. So this line means check if Y is equal to 1. This is a Boolean operation. And the Boolean operation is going to output true or false, 0 or 1. And I'm going to assign I'm going to assign the outcome of that operation to YB. So when I run this, hopefully unique YB, the B stands for binary, will be 0 or 1. So now what I've done is basically I've converted this from that crazy 16 class problem where I have 16 classes of Y into just a binary problem, arrhythmia or not. And now what I'm going to say is what I always do is figure out this is very well behaved. So now 54% of my Y's are equal to 1. So what does that mean about my data sample? So remember, 1 meant no arrhythmia. So that means that 54% of the 452 people did not have an arrhythmia. So balanced classes are good. There's a statistical argument for that. And there's also a kind of an intuitive argument. The intuitive argument, I'm not going to give you the statistical, but the intuitive argument is that, well, you want your classifier to see what the data looks like in each class. And you don't want it to be biased. Like if it was 99 to 1, then what ends up happening in your learning procedure is that it will kind of ignore the one. It won't weight the rare class as much in its learning, in its parameter fitting. So this is very nice. 54-46 is a great situation to be in. And let's visualize our X. I've done this already, and I know it doesn't look pretty, but we can make it look pretty. So this is, so the rows here are my individuals, and the columns here are my features. So you see that we have fallen prey to the color bar being automatically set to the max and the min in this array. But so what I do in this situation is min val is min apps or min x, and the colon here trend. You guys, anyone know what this operation does to x? Yeah, exactly. It's called Python calls that flattening. MATLAB, I think MATLAB uses that term too. Basically, MATLAB calls it vectorizing. So what I'm doing is I just want the biggest element in X, regardless of regardless of, right? And actually what I normally do is, I'm hurrying up because time is running out, but what I want to try to do, get a histogram of these. So most of the value, there's some outliers here, and that's what usually happens. So I'm going to constrain my values to be between negative, let's try negative 100 and 100. I'm going to post all this code. Everything I do in class, I'm going to post on Blackboard. So I'm going to try. Right. So this is a slightly better view of my data. Probably because the data is not. Yeah, it's getting there. Maybe clipping some of them. Right. So the color bar here is showing you the value of that feature for a given individual / arrhythmia variable. And so let's say the last thing I'll do is let's put up a conditional, let's put up what's called the class conditional histogram. So I'm going to say index healthy. I'm going to say it's YB is equal to 1. Yeah. So everything where y was 1, I'm going to call that healthy. And index unhealth or arrhythmia is equal to YB is not equal to 1. And now what I'm going to do is I'm going to show you a histogram. I'm going to pick one of the dimensions. I'm going to pick the first dimension. Oh, maybe not the first dimension. Let's do something that's not categorical.
Is this gonna work? Because it's only if it's exactly 1.
Yeah, but it is because it's YB is a Boolean. So I'm going to take dimension. Where's the QRS duration? Here, 5. So I'm going to plot. I'm going to make a histogram of all the QRS. How many? Say 20 bins. Well, yeah. Actually, let me just do it in separate. Overlaying histograms. What? It doesn't like hist? It's not recommended. Okay. Thanks for that. Okay. Oh, I didn't want to do that. I wanted the 5th dimension. Okay. I'm going to put titles on. This is after looking at I said that the first thing I always do is look at the class prevalence. See how many are in each class. The next thing I do is I just like look through the features and I see excellent. Yeah, exactly. Exactly. Right. So here I've made so you can see this would be a good, it will be a pretty good feature. I mean, it's not spectacular, but there's definitely outliers in the arrhythmia. Get rid of this, right? So you see all these individuals have a longer QRS duration and they have arrhythmia, right? Okay. I'm going to end class there. Thank you for watching. Don't forget to subscribe.